SwayamPrabha. Digital India. Educated India.
So now we'll be deriving the interface conditions for a free surface flow. Now let me explain what is a free surface flow and how does it differ from a conventional interfacial system or a multi-phase flow. Now to do this, I've taken a small sketch here. So what you're seeing in the sketch is a flow on down an incline. There's gravity downwards, and I have chosen the coordinate system x and y to align along the surface, that's x, and perpendicular to surface, the solid surface, is y. Now there is an arbitrary interface whose thickness is given by y equals h of x comma t, where h is the thickness of the film. Clearly I'm doing this problem in a two-dimensional setting. Nothing prevents me to go to a three-dimensional system, but just keep the equations and the derivation simple. I've kept it to a two-dimensional system. Now, the first step is to say what is a free surface flow. When I say a fluid, we are looking at a free surface flow, we mean that the gas above is passive. Let me write that down. The gas is passive. By passive, we mean that it does not dynamically affect the motion of the liquid below or the interface. So therefore, essentially the gas does not participate in the motion below, and that can only happen when the viscosity of the gas is neglected. So in other words, viscosity above, which you can say mu plus or mu g, is 0. The viscosity of the gas is completely 0. It is different from saying it's a vacuum. It's not a vacuum. It's just that it does not dynamically participate, but the gas can have a constant pressure, which you can call as P infinity. Okay, so I can say P infinity is constant. We also have a single fluid now, therefore I don't need to carry any subscripts for the liquid. So the viscosity of the liquid is mu and the density of the liquid is rho. So I've written down the governing equations for the liquid. These are just the mass and the momentum balance equations. The only difference is I've now written down the gravity terms, written as rho gx for the x component of the momentum, where gx is the gravity vector, component of gravity along x direction, and gy is the component of gravity in y direction. So we want to proceed further with solving these equations, for which we need the boundary conditions. So where do I apply the boundary conditions? We apply the boundary conditions at the surface, that is at the bottom, y equal to 0. We also have to apply boundary conditions or interface conditions at y equals h. So we have a moving boundary problem in other words. So let's now get the easy one out. We have the boundary conditions. Now the boundary conditions at y equal to 0. Remember, I have note that I have chosen the surface to be flat. Therefore, the boundary conditions are at y equal to 0. At y equal to 0, we have u equal to 0 and v equal to 0. So u equal to 0 is the no slip condition, and v equal to 0 is the no penetration condition. These are common boundary conditions that you would expect at solid surfaces, but these are not, of course, the only boundary conditions. You can have slip at a wall. So u equal to 0 is not satisfied in such systems. If it's a porous wall, you can even have fluid entering from the bottom. So therefore, v equal to 0 also would not be valid, but we will ignore those special cases for now. The focus is primarily on the interface conditions. Now let's look at the interface conditions. The interface conditions are at y equals h comma t. we want to derive these interface conditions. So what are the common interface conditions? Now, the first before we derive the interface conditions, we have to get the normal and the tangential vectors. Why do I need them? Because the interface conditions involve these unit normal vectors and unit tangent vectors. So let's consider a system again like this, the interface. I'm showing the coordinate system in the horizontal fashion, but this is identical to the sketch that I made below above. So I have an arbitrary interface like this. Now on this arbitrary interface, I have unit normal vector and tangent vector. Now, what's the definition of the interface? We define the interface as f of x comma y comma t, which is y minus h of x comma t is identical to 0. That's the definition of an interface. So what do I mean by that? If you're on the interface, f is 0. If you're below this interface, f is less than 0. Above the interface, f is greater than 0. Right? So we've already seen how to use this condition. So the normal vector n hat would be gradient of this f divided by magnitude of gradient, and that will be hxi plus j 1 plus hx square. We've already seen this earlier, so I'll not repeat it. Hx is a shorthand notation for dh by dx. Alright, so we will use this kind of shorthand notation wherever convenient. Similarly, we can write down the tangent vector as well. The tangent vector would be I hat plus hx j hat divided by square root of 1 plus hx square. Here I hat is unit vector in x direction and j hat is unit vector in y direction. So now that I have the two unit vectors, I can derive the curvature, the mean curvature, that will be del dot n, that will be del by del x of nx plus del by del y of ny, and nx would be the x component of the normal vector, and that's minus hx by square root of 1 plus hx square. Ny is 1 divided by square root of 1 plus hx square, and therefore I can just substitute this expression and I'm going to get minus hxx by 1 plus hx square whole power 3 by 2. So this is the definition of curvature in 2D. There are other ways to define curvature. This is the definition of the curvature if the interface is parameterized by this expression y equals h of x comma t. Okay. There are other ways to define curvature involving the angle that the interface makes to the horizontal and the arc length. So you could also define the curvature in terms of how this angle is changing. So something like d theta by ds and so on. Okay. So this is relevant, useful for us, so I'll stick to this. So what are the boundary conditions at an interface, or what are the interface conditions that I am interested in? So let's write down the usual ones. The first one would be normal stress balance. The normal stress balance would say, we have already derived this earlier. For students who may not be familiar with this, please go back to the lecture a few weeks ago where we derived the jump conditions at an interface. So n dot t dot n minus n dot t dot n plus where plus and minus refers to either side of the interface. This is equal to minus gamma times del dot n. Note that I have taken the interface, if you look at the original sketch, I have taken the interface to go from the normal vector to go from minus to plus. Okay, so minus is the liquid and plus is the gas above, right? So let's also define what is this T. T is the stress tensor, and this is nothing but it has a pressure part plus a strain rate part or the viscous part. Okay, so S is the strain rate tensor and I is the identity tensor. So I'm not writing this, I'm going to follow this kind of vector notation, the symbolic notation. I'm not going to use tensor notation or index notation for the benefit of students who may not be familiar with tensor notation, right? So let's basically write down the tangential stress balance as well. These are still general boundary conditions. We haven't applied it to this particular problem of a free surface flow. We'll do that in a minute. Plus minus del S of gamma, right? Now there is a third condition which is important, which is called the kinematic condition. So what does the kinematic condition says? The kinematic condition says if you are on the interface, then the motion of the interface is coupled to the fluid on either side of the interface, right? So let's look at this figure that we have here. We have defined the interface to be F is equal to 0, right? So every point on the interface will have F equal to 0, right? Let's consider an arbitrary point on this interface. Now, the material, since F is identically is equal to 0 for every material point on the interface, the material or substantial derivative of F with respect to time should be 0, right? In other words, if you are on the interface, any point on the interface will always have F equal to 0. Therefore, you have dF by dt is always equal to 0, and this essentially becomes del F by del T plus U del F by del X plus V del F by del Y is equal to 0. This is in a 2D setting, and therefore in a 2D setting we have, let's remember what is F. F is nothing but Y minus H of x comma t, which is 0. Therefore del F by del X is nothing but minus Hx. Del F by del Y is 1, right? And del F by del T, the partial derivative of F with respect to time, is nothing but minus Ht. So if I use this relationship, we have dF by dt is equal to 0 now becomes del H by del T plus U into del H by del T. I have a negative sign here. U del F by del X, that is U into minus del H by del X plus V into 1 is equal to 0. and therefore I have V is equal to del H by del T plus U del H by del X. Okay. This is referred to as the kinematic condition. This is a convenient way of writing it in 2D. But in 3D you have there are other ways to write it as well. I'll just do it in a minute. So what does it actually tell you is that the vertical velocity, that is V, that the vertical velocity is V, is coupled to the local motion velocity changes to H as well as the convective changes, which is U del H by del X. Okay. There are also other ways to write it. For example, remember that dF by dt is nothing but the partial derivative with respect to time as U dot grad F. Right? This is the definition of material derivative. Okay. Since n hat, the normal vector, we have already defined this to be gradient of f divided by magnitude of this gradient. We simply have the gradient of f is nothing but n hat magnitude of gradient. If I substitute this, we have del f by del t plus u dot gradient of f can be replaced with n hat gradient of f this is equal to 0, or I simply have u dot n will be minus 1 by gradient of f times the local changes in time for f, partial derivative of f with respect to time. This is another way of also writing down the jump conditions, the kinematic condition at the interface. U dot n will basically give me the normal component of the velocity. In this case, you can verify that that is exactly equal to v, and then the other term, the right hand side, will actually tell me that the local changes to the interface position. Okay. So we can also, this condition, the second condition, is especially useful when we say if the interface is fixed in position, fixed in space, then this condition simply becomes u dot n is equal to 0. So we've already derived the kinematic condition. This is for a condition where the interface is fixed in space. If the interface is fixed in space, any motion can at most be tangential to the surface, not normal to the surface. That is, the normal component has to be 0, right? But if the normal component is not 0 at an interface, then there is no other option but for the interface to move up and down. That's what the kinematic condition tells you. It's connected to the mass balance as well. Okay. Now let's derive the normal and the tangential stress balance. Let's return to these conditions. Now let's start with the normal stress balance condition. Right. So the normal stress balance condition, what do we have to do? We've already derived the general form of this equation. Let's write down this equation for a free surface. Okay. How do we do this? We first have to determine n dot t dot n. What is this? Okay. Now if I have to do it in a simple 2D, I have the advantage of using the expression definition of t in the matrix form, which is minus p times identity plus 2 mu times s, that is minus p times 1 0 0 1 and finally I have del v by del y is equal to 0. This is my stress tensor that I have at an interface. So now that I have the stress tensor, I can write down the expression of n dot t dot n using matrix multiplication. That would be nx ny the vector. This will be, remember, this is a row vector. So this is 1 cross 2, T11, T12, T21 and T22. That's the stress tensor. That's a 2 by 2 matrix. And finally I have Nx, Ny. That's a column vector, right? I would like all of you to try out this expression yourself. The Nx and Ny are just the x and y components of the normal vector. And what do I have here? If I substitute this, I get minus p plus 2 mu hx square by 1 plus hx square ux plus 1 by hx square u vy minus hx by 1 plus hx square into uy plus vx. So I'm using shorthand notation. Uy is nothing but del u by del y, ux is del u by del x, and vx is nothing but del v by del x, and vy is nothing but del v by del y. So I'm just using simple shorthand notation, subscript. I've already said hx is del h by del x. Okay, so we have from continuity equation we have uy plus vx is 0, and therefore I have vx is or vy is minus ux. Okay, so I have these conditions, and now I can simply write down n dot capital T dot n is minus p plus 2 mu by 1 plus hx square into small correction, sorry, the numerator will be hx square minus 1, and this will be ux, because I've now combined the first two terms using the relation vy is minus ux minus hx by 1 plus hx square uy plus vx. This is my normal stress balance. I can also similarly derive the expression n dot capital T dot T to be mu by 1 plus hx square uy mu by 1 plus hx square into uy plus vx times 1 minus hx square minus 4 ux hx. This is the expression of n dot capital T dot T. So now what we have now, we can write down the jump conditions at interface. So we have an interface which is at an angle like this. So I have, for the liquid below I have mu and rho. For the liquid above it is 0 and mu minus is mu. So for this such an interface I have normal stress balance. So we start by writing down the normal stress balance as n dot T dot T minus, that's the first term, So I have minus p plus 2 mu by 1 plus hx square hx square minus 1 into ux minus hx into uy plus vx. This whole thing is valid for a fluid below. That's minus. The fluid above has zero viscosity, so it's just minus p for the fluid above. This would be minus gamma times del dot n. So this simply becomes, if I combine the two terms, I have p infinity minus p plus 2 mu by 1 plus hx square into hx square minus 1 ux minus hx into uy plus vx of the, this is all for the fluid below, will be gamma times hxx by 1 plus hx square whole power 3 by 2. This is my normal stress balance. And what about the tangent stress balance? The tangent stress balance simply becomes, it's n dot t dot capital T dot the tangent vector t small t above, that is plus, minus n dot t minus, or let me write this down, n dot capital T dot t plus minus n dot capital T dot t minus, this will be equal to minus t hat dot del s of gamma. We know the Marangoni stress term is 0 since gamma is constant. We also know this term is 0 since mu of the fluid above is 0. So what do I simply have? We simply get mu by 1 plus hx square. This is the term we have already derived, n dot capital T dot small t, mu by hx square times uy plus vx times 1 minus hx square minus 4 ux hx is 0. Okay, we can even ignore that mu by 1 plus hx square so far. Okay, so when we write down the equations, so let's summarize the equations, summarize the interface conditions. So we have three interface conditions. One is the normal stress balance. These are interface conditions for a free surface flow. Again, ignoring Marangoni effects, so gamma is constant. What are the interface conditions? Normal stress balance. The normal stress balance essentially says that the pressure above minus the pressure below, all of these conditions are at y equals h of x comma t. They are only applicable at y equals h comma t. So when we refer to the pressure in this condition, we mean it's the pressure at the interface, just below the interface. Okay, so P infinity minus P plus 2 mu times hx square minus 1 by 1 plus hx square ux minus hx by 1 plus hx square uy plus vx. This will be equal to gamma hxx by 1 plus hx square whole power 3 by 2. That's the first condition. The tangent stress condition, the tangent stress balance essentially reduces to uy plus vx of 1 minus hx square minus 4 ux hx is equal to 0. That's a tangent stress condition. And finally we have the kinematic condition. Kinematic condition, we have u dot n at the interface will be minus 1 by grand f times del f by del t, or a more convenient way to do this is the vertical velocity of the interface will be del h by del t plus u del h by del x, right? So now we have these three conditions. We have to couple them with the interface, the fluid equations, the governing equations of fluid and the boundary condition at the bottom, and this would provide a complete closed set of equations that can be solved. So these, of course, these equations that we have just derived and the boundary conditions, they are non-linear. You can see several places you have products of hx with itself. So this makes it non-linear. That's non-linear in the curvature term also on the right hand side that you can see in the normal stress balance. The governing equations themselves are non-linear. The governing equations themselves are non-linear. So when we apply lubrication approximation, or when we apply some special conditions such as fully developed flow and things like that, then of course the equations would significantly simplify. So we will see several examples where we will take these equations and solve simplified version of these equations for various applications, right? So thank you.